Well, greetings, mathletes, and welcome back. Um, so today we're going to be talking about how to count. This is not your typical counting. This is, well, you'll see. So, in any case, there's uh, there's four main things that we're going to be taking a look at today. So, the first thing is called the multiplication. Oh, it turns out this thing works better when I turn it to a pencil. Let's try this one more time. Okay, so the first thing we're going to be talking about is called the multiplication principle. Wow, work on my spelling principle too. Right, so the multiplication principle is going to be the first thing that we deal with, and what that handles are independent choices. Right, so this also has to do with making decisions and all that kind of stuff, but it's more about counting how many possibilities there are for an outcome. Okay, so and we'll go into more detail on this. I'm giving you the rundown right now. Then we want to know how to arrange n items. Oops. Right? We want to know how to arrange n items. We have a class of 30 students. How many ways can they line up? Right? Every way that they line up is a different arrangement of the students. So we want to know how to be able to deal with stuff like that. Then we want to talk about how to arrange n items r at a time. Okay, I have 30 kids in the class, but I'm only going to have 5 of them line up. How many different possibilities are there for 5 children in a line when you have 30 to pick from? So that's another way to look at it. And if you think about it, there's actually a whole lot of choices in that. And here, when we say arrange, that means the order that people line up is important, right? So if you swap any two students, that's a different arrangement. Okay, but if order doesn't matter, there's a different thing that we talk about. We don't say we're arranging, we say we're choosing choosing our items from n choices. Right? So that's one of those things where let's say you have the 30 students in a class, you're choosing 5 of them to do something, and it doesn't matter what order you choose them in. It's if you have the same 5 students, it's the same 5 students. The lottery works like this, right? It doesn't matter what order the numbers come up in. It's just a matter of whether you have those 5 numbers or however many numbers are in the lottery. So those are the things that we're going to be talking about today. So let's go ahead and take a look at some of them. So let's go ahead and delete all of that business. And so we'll start with talking about the multiplication principle. Right? And the multiplication principle basically says that if you have several choices that are that don't affect each other, they're independent choices, and you have a set number of options for each choice, what you do if you want your total number of choices is you multiply all the numbers of options at each stage. Now, that sounded that was very wordy. I think it's going to make a lot more sense if we actually see it. So let's say we're choosing an outfit. Right? So we're choosing an outfit to wear. We have 3 shirts to choose from, and there's 4 pairs of pants. Right? So let's look at this. So at the first choice, you have, I'm going to, in fact, just to make this easier, let me do this real quick. 3 shirts, I'll call it shirt 1, shirt 2, and shirt 3, just so I don't have to write the word shirt. And then pants, we'll do pants 1, pants 2, pants 3, and pants 4, right? So those are the different choices we have. So I'm going to start by using a tree diagram to show how they all pair up. So basically, to start out with, we have our first choice, which is shirt 1, shirt 2, or shirt 3, right? You're going to pick a shirt. Now, we are completely disregarding whether these things match or whether you would actually wear them together. We're just talking about an outfit, period. There's no aesthetics here. So, if I pick shirt 1, I still have to choose a pair of pants. I have 4 choices for pants. 1, 2, 3, 4. So P1, P2, P3, P4. Okay, so that's 4 choices. If I pick shirt 2, I still have the same 4 choices for pants. And if I pick shirt 3, oh, yikes, let's try that again. There we go. P1, P2, P3, and P4, right? So for these 3 choices, for the 3 choices of shirts, once I make those, for each one of those, there are 4 choices of pants. So the total number of outfits you can make, you have 4 that go with shirt 1, you have 4 that go with shirt 2, 4 that go with shirt 3. And so really what I've done is I've taken and broken this into 2 choices. The first choice is the choice of shirt, and I have 3 possibilities there. The second choice is the choice of pants, and I have 4 possibilities there. And I can either see by counting all the endpoints here, or by multiplying this out, that I have 12 different outfits I can wear. Now, if we wanted to throw 5 hats in there too, so after you choose shirt, pants, you now have to choose hats. It would be 3 times 4, and if there were 5 hats, it would be times 5, right? So there would be 60 choices. So this thing keeps changing. Depending on how many choices you have for each thing, for each step, I should say, you just end up multiplying all the possibilities of each choice together. That's essentially what the idea is. So I like to put these slots down so I can fill the slot with the number of choices, knowing that I'm going to multiply as I go. Okay, so that's the multiplication principle. And let's see here. We're actually going to revisit all of these ideas at the end and see if we can tell when to use which idea as we go. So there will be more examples. I want to get through these main 4 things first, and then we'll talk about how they fit together in examples and how you know which one to use. Okay, so let's go ahead and clear that. Now, so let's suppose there's, oh, here we go again with the choosing the wrong thing. You have 5 athletes or mathletes in a foot race. Assume no ties, right? So you can always tell who comes in first, second, third, fourth, and fifth. Okay. What are the orders that they could? What are the orders? How many different ways could they finish the race? Right. So we want to know how many different orders they can finish in. Now, this one's a little touchy. It's kind of funny because it doesn't. When you start thinking about your choices, it feels a little bit weird. Um, so here's how it ends up working out. You have 5 slots. You have first place, second place, third place, fourth place, fifth place, right? So let's go through and look at what our possibilities are for each choice. Now, if we look at first place, we haven't chosen any of the other spots yet, and it really doesn't matter which order we do this in. It'll end up the same way, but I like to start with first place. So if I start with first place, we want to ask ourselves, how many choices do I have for first place? Well, there's 5 competitors. Any one of those 5 could finish first. So there are 5 choices for first place. In fact, let me write that in. Okay. Now, someone has finished first, and it doesn't matter who it is, but someone finished first, and that person is not going to be coming in second place. So the number of choices we have for second place is 4, because one person is taken out of the pool now because they already finished. So there are 4 choices for second place. Now, when we go down to third place, first and second place have already been chosen, so 2 people have been taken out of this pool, which means that there are 3 choices left for third place. For fourth place, we have 3 competitors taken out of this race already by getting first, second, and third. So that means there are 2 choices left for fourth place. And then for fifth place, the first 4 places are already taken. There's only 1 choice left for fifth place. And so what we've done is we've essentially gone 5 times 4 times 3 times 2 times 1. And that computation, taking a number and then multiplying it by every integer less than that number, pops up often enough that we have a function for it. It's called the factorial function. And so this right here, this quantity, this whole thing here, would represent 5 factorial. It's represented with an exclamation point. So this factorial is super important when it comes to counting. It shows up in everything as far as keeping track of this stuff. So if you guys go on to take like a probability and statistics course, this thing is going to show up a lot. So if you're not familiar with it, poke around with it, practice a little bit. Excuse me. Yeah, so just to give you an example, if I had something like 3 factorial, this would be 3 times 2 times 1, right? That ends up being 6. If I multiplied all this out, I believe that comes out to 120. Yeah, that's 20, that's 6, so it's going to be 120. So for the number of ways people can finish this race here, if I multiply all that out, there's 120 choices. And furthermore, you can actually do this factorial thing on your calculator. And I just want to show you this. Actually, I'm kind of excited about this because I just got this calculator emulator. Ta-da! There it is. So let's go ahead, and this thing's exactly like a calculator. I even have to turn it on because it turns off if I leave it idle. Okay, so if we want to punch in 5 factorial, and actually, let's do this so you can see it a little bit better. I'm going to shrink that down just a hair. Back. There we go. Now, here's how you find it. So you start out with the 5. Okay, now this is for a TI-84. Most of the TI graphing calculators do the same thing. So this should match up if you have a TI graphing calculator. If you don't, if you have another calculator, there's usually a button that says probability or PRB or something like that. For the TI, you find the factorial under math, and then you move to the right across the top. I'm using the arrows here on the calculator to probability, and you notice that the 4th one down, sorry, I was trying to draw on it, I guess I'm going to move it, is a factorial. It's a little exclamation point. So what you want to do then is hit the number 4, and then enters 5 factorial, and then you hit enter, and it spits out the correct answer. And you could also, you could do this. Oops, I think I hit divided on those last few. Let's try that again. There we go. And it should come out to 120 also, right? So it is doing what it says it does. Now, factorials are kind of interesting because they get really big really fast. I was doing some experiments with this, and the highest number that your calculator will handle, and some of yours may not even handle this, but if you do 69 factorial, the calculator will give it to you. And notice that's in scientific notation, how big that number is. So if you had 69 competitors and wanted to know the number of answers, is approximately 1.7 times 10 to the 98th power. So that's basically a 1 with 98 zeros following it. That's a really, really big number. It'd take you a while to write it down. Um, but the calculator's still handling it. If you go to 70 factorial, it basically tells you to go away. It says, I can't do that. It's an overflow. The number's too big. So just be aware that these don't always handle super, super nice. So let me go ahead and clear that out and get back here. And there's actually other things you can do to get a hold of these things. But that's how you enter a factorial in your calculator. You want to be able to do this. You're going to need this for the next exam. So if you can't find it on your calculator, definitely come and see me so that I can explain it to you, so I can help you find all that stuff. All right. Okay, so that's the multiplication principle. So let's go ahead and clear this out. Okay, so this next example, to lead into the next function we're talking about, I want to change this up. We're kind of using the same thing. It's still a foot race. Oh yeah, I still have to turn on the pencil. Right, 5 places are recorded. Right, so the only ones who count are first through 5th place. But this time, there are 9 competitors. Okay, so first of all, you do have the tools at this point to figure this out. So what I'd like you to do is see if you can work out something on your own, and then look at my explanation to see if that matches up with how the way you thought about it, and then you can correct any differences. So go ahead and pause here and see if you can work it out. Okay, so let's go ahead and take a look. Since 5 places are being recorded, that means there are 5 slots to deal with, right? Just like before, it's not really much different. So you have first, second, third. Oh, my pen's taking a second to show up for me. First, second, third, fourth, fifth. And let's look at what choices we have now. So for first place, there are 9 choices. There's 9 competitors. So that goes into our first spot. And if we used one up on the first place, that means there are 8 left to have second place, right? 8 left to choose from for second place. And then for third place, there are 7 choices. For fourth place, there are 6 choices. And for fifth place, there are 5 choices, and it stops. And you notice it's not really quite the same as 9 factorial, because that would continue with 4, 3, 2, 1, right? So what we end up with is 9 times 8 times 7 times 6 times 5. And if we want to work that out, where'd I put my emulator? There we go. I'm just going to work it out on the screen here. We got 9 times 8 times 7 times 6 times 5. And what that gives me, oops, let's pull that back up. is 15,120. Sorry, that keeps disappearing. It's because it's in a different window. And so as soon as I touch this one, it goes to the background. Now, so here's the question is there a nicer way to do this? Because it'd be really nice to be able to do this when you have, oh, say, 100 competitors and you need to choose 50 of them, which is not very reasonable to plug into a calculator. You know, 50 times 49 times 48, all the way down. Um, yeah, that would be very, very painful. So we need to see if we can build something else here. So this certainly looks like a 9 factorial. And so what I'm going to do is I'm going to write the whole thing out in terms of factorials. I have 9 factorial here, and I know that is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Woo! Let's put a division there. Okay, so here's the problem. I have too much stuff here. I only need this down to the 5, right? This piece is more than I need. I need to get rid of it. Well, all of these things are being multiplied. So if I went ahead and just divided the whole thing by 4 times 3 times 2 times 1, that would work. And you notice this is now 9 factorial divided by 4 factorial, right? Dividing it by that 4 factorial basically cancels these 4 things, and it leaves me with exactly what I want, right? That piece right there. Now, this has a name, right? And in fact, it has a formula too. So before, when we were dealing with n things and we wanted to see all the arrangements of the whole set of n things, we just looked at n factorial. But if I want to see the arrangement of those n things a smaller number of times, like in smaller groups, I have to use this. And this is actually called a permutation. Let me write the definition over here. Okay, so a permutation, first of all, we are taking 9 things and we're doing it 5 of them at a time, right? So that's the first thing to notice. So the notation for writing it is I have 9 things, I write a capital P, and I want to take them 5 at a time. That's the notation. The formula for this, which would be NPR, that has nothing to do with National Public Radio now. It turns out that it is n factorial over n minus r factorial. So there's 2 factorials in it. Let's see how that matches up over here. Right? So that would be 9. Well, actually, first of all, we're taking 9 things 5 at a time. Right? So that's 9p5. So that would be 9 factorial over 9 minus 5 factorial. Well, 9 minus 5 is 4, isn't it? So this is 9 factorial over 4 factorial, which is exactly what I wanted. And you can see that the way that works out, because we just worked it out here. Oof, that's a horrible arrow. Let's try that again. There. That looks better. Okay, so this is what happens when you just need to get a group of 9 people, and it matters which order they're sitting in, right? So let's see here. Yeah, let's go ahead and go to the last thing. So the last case here is when order doesn't matter. So let's say it's that same race. You have, let's see, how many competitors do we have? 9? Nope. And it turns out that, once again, turning on the pencil helps. So let's say we have 9 competitors. And the coach needs 5 to stay for cleanup. Ugh. Sometimes these controls are just too sensitive. There we go. Okay, so we need 5 to stay for cleanup. Now, here's the thing. The first person chosen to stay for cleanup isn't going to be any different than the second person chosen for cleanup. They're identical positions. It's not like first, second, third, fourth, fifth, where there's a definite spot, and if you swap 2 people, it's different. It doesn't matter if you got picked first or fifth for cleanup, you're still on cleanup, right? There's no difference. So here, order doesn't matter. So it doesn't matter what order they're picked in. Really, what we're trying to do is find a group of 5. We're really asking ourselves how many different groups. Actually, I didn't even ask the question. I just realized that. What I wanted to know is how many different ways that we could pick 5 of these competitors to stay after and help clean. So order doesn't matter here. And when order doesn't matter, it's something called a combination. Right? And so if I have n things, if I'm using a combination to choose r things from n things, right? So there's r, in this case, it's going to be 5 for r and 9 for n. So this is 9CR. And actually, the way you say it when you speak is you say n choose r, or 9 choose 5. I was thinking 5. There we go. Or 9 choose 5. Now, the way it works is actually very similar to the NPR, but there's one little tweak to it because we have to take out the fact that order matters with NPR. The formula for this, you start with your n factorial on top, and you definitely have your n minus r factorial, but since we're choosing things r at a time, we need to take out all the repeats because the way I have it written right now, it's distinguishing orders. So if Bob gets chosen to be in the set, this is actually counting 5 different ways that he is in the set. That's too many ways because he can occupy any of those positions: first, second, third, fourth, fifth. And this is counting those as different, but they're not different. So what you have to do is divide out by the number of things you're choosing. And so this ends up being the entire formula. If I were to write this whole thing out, it would be 9 factorial over, 5 minus 9 is 4 over 4 factorial. And then r is 5, so it would be over 5 factorial. And it'll be a smaller number than the permutation, right? I hope I used that word. NPR is called a permutation, by the way. Right? And these are called combinations. So let's see if we can go ahead and calculate that. See what it comes out to, because it's going to be a pretty big number. All right, so actually let's scoot this over here so we can see what we're doing. So we turn this on, and let's see here. We have 9 factorial divided by, and you have to use parentheses on this because otherwise it will only divide the first factorial and then multiply the second one instead of dividing it also. It would be 4 factorial five factorial. Oh, I can't click that. And then close your parentheses. So that way it's dividing by both of the factorials. And ba-boom, I get 126. Now, I want to show you something else here. Because we worked out 9p5, and we worked out 9c5, right? Okay, you can plug these into your calculator as well. If I remember correctly, this came out to 15,120, and then this one we just worked out is 126, right? So let me show you how this works on the calculator now. Because you'll notice that there are, let's see here, let's do NPR first. Let me scoot this back over here so we can see these guys. So I would start with the 9, right? Because I'm doing this one right now. That calculator. So I'm doing this one right now. Okay. Now I need to find NPR. And so we go in here again. We go to probability, and you notice the second choice says NPR. So we can hit 2, and then we need the second number, which in this case is 5, and then we hit enter, and then we get 15,120. So it plugs directly into the calculator, right? It's not a problem. Now you notice that what's written in the calculator does not match what is written here on the screen. This is how you write it in print. This is how you enter it into the calculator. You notice there's no N and R in the written version of this. That's just the way they put the symbol into the calculator. So you put N first, then the NPR, then the 5. Let's try it with NCR, see if we get 126. So I'll need the 9, and then math, probability, and then you notice the third choice is NCR. So we'll go 3, and then we want to choose 5, and enter, and we get 126. So we have shortcuts for all of this stuff. You don't have to enter them all in individually, which is kind of nice, actually. Okay. Excuse me. So let's go ahead and minimize that. And now let's take a look at a few examples. I want to look at a couple of examples so we can tell which ones of these to use in what kinds of conditions. And then I want to talk a little bit about one more type of counting situation. And that's where you happen to have things that are identical. Usually the classic example is scrambling the letters in the word Mississippi, right? You have a lot of repeat letters in there, right? The MISS. If you swap those two S's, you can't tell the difference. And so you have to be able to accommodate that fact. So we'll be taking a look at those too. So let's go ahead and clear this off. And I just kind of want to summarize here. So if I have distinct choices, oh, I keep doing that. Let's try this again. If I have distinct choices with a specific number of possibilities at each choice, I'm going to use the multiplication principle. Right? We'll use the multiplication principle for that. That's like when we had the different shirts, different pants, and all that kind of stuff. Each one of those choices is distinct from the other ones, and so we end up multiplying the possible choices at each level. Now, if order matters, there's a couple of situations. One, you have n items. Let's actually put it this way. If you have the arrangement of n items, right? How many ways can you scramble these things? Where you're using all of the items every single time. That ends up just being n factorial. Okay? Right? So that's our first thing. Then we have the arrangement of n items are at a time. That's where we're looking at 9 competitors, but only 5 of them are going to place, right? And so we have n items, 9 items in this case, because there's 5 places, we're arranging them 5 at a time. So that would be your NPR. Right? This is where order matters. And then when order doesn't matter, and when I say order, it's also placement, right? Order could be who has what job. Picking 3 people to be president, vice president, and treasurer, right? Those are different positions. So if you swap any of them, it changes. That would be somewhere where order matters. But if you're picking 3 representatives to sit on a committee and there's no difference between them, order doesn't matter. And when order doesn't matter, and you're doing n items r at a time, it is NCR, right? So this is N choose R. And that is when you're just looking for a group of things. Again, a good example is lottery ticket, because it doesn't matter what order those numbers pop up. Once they're chosen, they're chosen. And if you have all of the numbers, you're a winner. It doesn't matter if you didn't pick those numbers in the same order that they came out of the hopper. So okay, so that's our rundown on what we've looked at so far. We actually do still have a little piece to talk about that has to do with counting, but these are the main formulas that we're looking at. So if you have distinct choices and there's no real pattern to it, you can just go back and use the multiplication principle. Notice the multiplication principle is what led us to this factorial, and it also led us, and from the factorial, it led us over to the permutation. Combinations, it's actually part of that too. I didn't go into a lot of explanation on it. I more just threw it at you. But combinations also basically all come out of the multiplication principle, basic counting principles. All right, so what I want to do now is I want to take a little time to look at some examples of this and just see what we can do with it. See if we can tell what to use where. Okay, so let me go ahead and clear this off. Okay, so here's our first question. Ms. Statsy has a 3rd grade class who is returning from recess. There are 15 students in the class. How many different arrangements can her class line up? Well, I think it'd probably be best to see if you guys can work on it on your own first. Let's see if you can reason it out, figure out which method you're going to use and all that kind of stuff, and then walk through and see if you can find the answer. And then we'll work it out together. So go ahead and pause here and see if you can do it yourself. Okay. So let's see what we got here. So we got 15 students, and we're talking about how many different ways they can line up. And this is using all of the students, right? It's all 15 students. Every swapping of 2 students would be a different way to line up. So order matters. So that's the first thing to notice, is that order matters. So that means it's either the n factorial or NPR. So let's see, we're using everybody in the class. So that means it's a factorial, which means that the answer to this is 15 factorial. And so let's see what that actually is. So let's go and turn that back on. We'll go 15 math. Oops, I guess I have to move that. There, I'll just sit over here in the middle for a while. Let's see here. We want to go to probability and then to 4. So 15 factorial is going to be a big number. Holy cow. Let's see here. That is in scientific notation. So let's go ahead and talk about what that actually means. I'm just going to write down everything I see here and make sure that we understand what it means. So we have, I lost it. That's it. Let's do this. This way I can see it still. I think I have it figured out now. Okay, so you got 1.3076, and that e to e12, actually what it means is times 10 to the 12th. Well, every time you multiply by 10, it moves the decimal one place. So if I multiply it by 10 12 times, that means it's moving the decimal 12 places. So that means we go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I need zeros for 10, 11, and 12. So let's write down this whole number. 13076 Oh, try that again. Let's see. So 30767436800. So now we need to put in our commas. And just looking at this, you have thousands, millions, billions. This is over 1 trillion different combinations as far as the number of ways that students can line up. That's actually pretty impressive. But that's what that means. When you see something show up in scientific notation like that, where you have the E12, that just means if a positive number means move the decimal place in the positive direction to the right. If you have a negative number, you move it to the left. All right, so yeah, that's a really big number. And in fact, in math papers and things like that, oftentimes they'll just write 15 factorial. They don't even bother working the rest of it out. They just assume the reader can do it themselves. Okay, so let's go ahead and look at the next example here and see what we got here. So let's go ahead and clear this off. Delete that. All right, so we're still working on Mrs. Statsy here. So when class begins, she realizes that she left her coffee and the copies of the worksheets for the class that day. She chooses one student to get her coffee and one to get her copies. How many ways can she do this? Now, we're still assuming there's 15 students in the class, right? But I need to choose one to do copies and one to get the coffee. And it doesn't matter. Well, it does matter. It's a different choice if Susie gets the coffee and Joe gets the copies than if Joe gets the coffee and Susie gets the copies, right? So those are two different choices, and they're distinct. So there's two ways to look at this. We can actually do it through the multiplication principle. It's probably the most direct one. Let's say the first thing is coffee and then copies. Okay, so we want to figure out how many students she has to choose from to go get her coffee. Well, there are 15 students to choose from. Once she has chosen one to get her coffee, she has to choose a different student to get her copies. There are 14 students left to choose from. And so I end up with 15 times 14, which, let's see, 225. So that's what, 211? No, that's not right. Let's just work that out. $15 times 14. Oh, I just did 14 times 14. Let's try that again. They don't hand these degrees out to anybody, man. 210. Okay, so there are 210 distinct ways that she can choose a student to get her coffee and a student to get her copies. Now, you might have been thinking, order matters. I'm not choosing the whole class. Why couldn't I have said that this is 15 choose 2? Well, you can actually. Oh, excuse me, permuted by 2. Wrong one. Order does matter here. Right? 15 permuted by 2. Let's actually just look at the formula. You'll see that it comes down to this again. right? So first of all, if I use the formula, the top would be 15 factorial, and the bottom would be 15 minus 2 factorial. So that means I'm 15 factorial over 13 factorial. Well, remember 15 factorial times 13 and times 12 dot dot dot, and it's going to go on all the way down to 1, right? That's supposed to be a dot 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 in there, but I kind of scrolled the screen instead. On the bottom, there's 13 factorial, which is 13 times 12 times dot dot dot. Well, these guys cancel. Everything 13 and less will cancel out, and I'm left with 15 times 14, which is exactly what we got using the multiplication principle. So they're very closely tied together, right? 15 permuted by 2 is the same thing as 15 times 14, right? So this is what you should have gotten as far as working this one out. You should get that there are 210 ways for her to do this. Notice we're getting a lot of different ways to do things, even though we have a fairly small class. There's only 15 students in this class. It's really kind of interesting. Okay, so let's go ahead and look at the next example here. So we'll go ahead and clear this one off. Okay, so here's the next one. So later that day, and we're still assuming this is all the same class. Later that day, they began to talk about student government. For the council, for the student council, the class needs to elect 3 representatives. How many ways can this be done? Now, you notice they're just representatives. We're not talking about specific offices. These are all the same office, right? When you're talking about class representatives, you're just sitting on the committee. That's it. There's no distinction between one representative and the other. Okay. So, see what you can do with this one. So go ahead and pause here and see if you can come up with the answer. Okay. Now, let's take a look at this. So we have the 15 students in the class, and I need 3 of them to be on the student council. Order does not matter in this case, right? I need to choose 3 students out of this, and it doesn't matter what order they're being chosen in. And so that means it's a combination. And so what I'm going to be looking at, and I keep doing that, let's try this again, is 15 choose 3. That's really what we're looking at right now. So you could certainly do this and go through the whole business. 15 minus 3 factorial, and then 3 factorial, right? That's quite a business. And I'm just going to show you this once, just so you can see how these things get computed by hand, because calculators weren't always all over the place. People didn't always walk around with a calculator on their phone and everything else. Usually you just had to work things out. So let me just show you how this works. With these factorials, it turns out that you can cancel out stuff everywhere. So 15 minus 3 factorial, let's see here, that's going to be 12 factorial. And then we have 3 factorial. Everything in the denominator always cancels out with these factorial problems. So if I look at what this actually is, this is 15 times 14 times 13 times 12 times 11 times 10 times... Do I want to write all that out? I don't know. And I'll just put a dot, dot, dot in there because that goes on forever. And then underneath, I have 12 times 11 times 10 times 9, dot, 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 right? And then 3 factorial, 3 times 2 times 1. So I'm expanding everything out. And actually, as a problem-solving technique, this is called expanding the definition. Now, 12, 11, 12 and everything less than 12 are going to cancel out, right? So I can do this and that just to start off with. Now the only thing I have left with this 3 times 2 times 1. Well, 2 goes into 14 7 times. 3 goes into 15 5 times, and now I can multiply 7 times 5 times 13, right? So if I work that out, let's go ahead and pull this guy back up. 7 times 5 times 13, I get 455. Okay, now we want to see if that comes out the same when we use the NCR formula. So let's see what we got. So we are doing 15 choose 3. So 15 math probability. I want 3 for NCR, and it's choose 3, and we hit enter, and we get 455 again, right? So the calculator saves us a lot of time as far as that goes. Now, so hopefully you got through that okay. The main thing to note in this is that when order doesn't matter, if you can distinguish that it doesn't matter which order you choose things in, then you use combinations, right? You use the NCR. If the order does matter or the positions are distinct, then you use NPR or N factorial. And actually, if even using NPR, if I use NPN, that's just the same as N factorial. That's just a little extra information, but it does show up. And actually something else that may show up at some point that I didn't mention, there are two very weird, well, one particular weird thing with factorials. One, if you look at 1 factorial, you're really not multiplying it by anything, right? So it seems kind of weird to talk about it because times what? There's nothing less than 1. But it does kind of make sense to say that it's equal to 1, right? But the other thing is 0 factorial. That is a very strange little beast. The reason for it is actually fairly obnoxious. It has to do with stuff that I didn't see until after my 3rd semester of calculus. I didn't see it till I took differential equations. But the factorial is actually defined in terms of another function that does have values at 0. So what it ends up being with 0 factorial is 0 factorial also gives you 1. It's a very strange little computation, right? But you should know that. Just because if it comes up, you should know it's 1. All right. Now let's look at the last example here. Okay, so for this next example here, we're looking at, let's see, Mrs. Statsy holds a race, and this is obviously a race. Well, I don't know if it's obvious or not, but it's a race between the students, right? So she holds a race, and there's a clear first place and second place, but there's a 3-way tie for 3rd place. How many ways can this happen in a class of 15 students? So there's kind of a couple of different things that happen here. There's actually several different ways to look at it. Actually, before we even start, go ahead and pause here and see if you can work it out first. Okay, so now that you've taken a stab at it, I look at it this way. I'll probably take more than one view of this just because. I can look at the number of choices for first place, the number of choices for second place, and the number of ways that I can have a 3-way tie between the students that are left. So this is first, second, and 3-way tie. Okay, so there's 15 choices for first place, right? No problem there. If I choose something for first place, there are 14 choices for second place. Okay, so those are clearly going to be multiplied. What I need to figure out, if I can figure out the number of 3-way ties there can be among who is left, then I can just multiply that number in. Well, if it's a tie, there's no order, right? Everybody finished simultaneously, so all three of them got third place. And there's 13 students left. So what that ends up being is 13 choose 3. So my computation for the number of ways that this race could be finished with a clear first, a clear second, and a three-way tie for third is 15 times 14 times 13 choose 3. We can plug that in into the calculator directly. Right? We got 15 times 14 times, and it's a good idea to use the parentheses on this. We have 13 students left, and we got to go math, probability, let's see, combination, 3, and close our parentheses, and we get 60,060. Right? That's a lot of different ways you can finish. Now, the other way you can look at this, if I'm just looking at first and second place as a single event, you could have also looked at this as two things. The first event is clear first and second place. The second event is a three-way tie for third. Clear first and second place is 15 permuted by 2, right? Because order matters there. I've taken 2 out, so now what's left is 13 choose 3. And for the same reason as far as the three-way tie. If you plug this into the calculator, you'll see you get the same answer. Right? So let's go ahead and do that here. So we have, let's see here, where to go. 15 math, we'll go probability, we want 3. Oh, I did the wrong one. Doggone it. Can I delete there? Yeah, there we go. So we want math, probability. I want 2, excuse me. The first one is NPR. Right? So it's 15 permuted by 2. We get an answer for that. And then we go times, and you notice that little answer thing. What that means is it's taking the last answer it spit out. And then we can choose, let's see, I have 13. Wait. Choose 3. And then close our parentheses. Because if you don't put the parentheses, you run the danger of just multiplying the 13 by the answer and then using that in the combination. And you notice we get the exact same answer. So that one we did NPR times NCR to get that. So there's more than one way to reason these. As long as you're using correct counting tools, you should be fine. Okay, so let's go ahead and pause. Excuse me. Let's go ahead and clear this out, and then go ahead and look at our last counting example. Okay, so the last thing is, it's more of an exercise just to kind of get you used to having to count in weird ways. But, looking at a word like, let's pick something nice. Okay, how about the word nice? Right? If we're wondering how many different ways we can arrange the letters in the word nice, right? You can actually think of it the same way that you think about, lining students up in a line or anything else. I have 4 distinct things, right? And I'm trying to put them into 4 positions in all the ways possible. So that ends up being 4 factorial, right? Okay, now, if I take something like the word garbage, okay, we have a problem here. this right here, the two G's, if I swap those, if I change that order, it doesn't change anything. That's exactly identical to the original word. Same thing with the A's, right? If I go ahead and swap those two A's, it doesn't change anything. So those are problems because they're not distinct. So here's how we handle it. So the first thing we want to do is look at how many letters we have total, right? No matter whether they repeat themselves or not. We're going to take a look at the total number of letters. In this case, it is 7. So I'm definitely starting with 7 factorial. But what you end up having to do is anything that repeats, you have to divide out. And it's always by the factorial of how many times it appears. So G appears twice. So to compensate for that, we have to divide out by 2 factorial, right? That is for the G. That handles where the G is, or how many times the G repeats itself. Then we need to also distinguish, we need to also note that there's no distinction if I swap the A's. Well, there's 2 A's. So that means I divide out by 2 factorial again. So once for the G's, once for the A's, and then what I get is the number of ways I can rearrange whatever's left. So if I go ahead and do that, 7 factorial over 2 factorial over times 2 factorial, let's see here. Let's go ahead and pull up the calculator. So we'll go 7 math, probability, factorial, divided by, anytime you're dividing by multiple factorials, it's a good idea to put parentheses around that entire denominator. So that's divided by 2 factorial, and I need one more 2 factorial. So I'm going to put that in and then close my parentheses. And so what I get is that I lost it. Okay, what I get is that there are 1,260 different ways to arrange these letters. Now, if you have letters that show up more than twice, if it shows up 3 times, then you would divide by a 3 factorial. If the letter shows up 5 times, you divide by 5 factorial. And so the classic example really is to take the letters in Mississippi and figure out how many different ways, how many distinct ways that you can arrange these things. So the first thing you have to figure out is how many letters you have. Actually, I think you guys should at least try this and see if your suspicions are correct with the way this works. See if you can at least write down the expression in terms of factorials that describes how many different arrangements we have here. Go ahead and pause it here. Okay. So I'm assuming you've already tried it out. Let's see what we got. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So that means whatever we're doing, we're starting with 11 factorial. Okay. So now I have to go through and figure out my repeat letters. The only letter that doesn't repeat is M. Everything else repeats. So M, I don't need to compensate for M because it only shows up one time. I, let's see, 1, 2, 3, 4. I shows up 4 times, so I have to divide by 4 factorial. Okay, so we've taken care of the I's now. Let's look at the S's. Well, S's show up 4 times, so I have to divide by another 4 factorial. Okay, and let's see, I've taken care of I's and S's. Now I have P's, and I have to divide out the repeats for the P's, which is going to be 2 factorial. And that's what your expression should look like. You should have 11 factorial divided by 4 factorial, 4 factorial, 2 factorial. Right? So let's see how that comes out. That's going to be a really big number. Oh, you know what? Just for fun, I'm going to work this out by hand. I haven't had enough fun today. So let's go ahead and do that. I'm going to just work this one out by hand. We'll check it on the calculator, make sure we did it right. So we have 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's my numerator. You can see why we've learned to have a shorthand for this. Then 4 factorial. Then another 4 factorial. Oops. Then a 2 factorial. Okay, so let's switch colors here and see what we can get. So I can take these and kill those, no problem. The rest of these, let's see, 4 it goes into 8 twice. 3 goes into 6 twice. 2 goes into 10 twice. Okay, so that one's taken care of. Now I just need to take care of this other 2. Well, I can just cancel out one of my 2's. Okay, so let's look at what I have left in the numerator here. I have 11 times 5 times 9 times 2. Oops, let me back that up so I can have enough room. So 11 times 5 times 9 times 2 times 7 times 5. Woo! And that's it. That's the whole thing. We just have to multiply those guys together. So let's see here. That is something I'm going to do on the calculator. Probably do it in my head, but let's scoot this guy over. So we got 11 times 5 times 9 times 2 times 7 times 5. Woo! Okay, so we get 34,650. It's quite a number. Let's make sure we get the same thing if we use the factorials in the calculator. So we'll go 11 math probability factorial divided by, and we got to use parentheses here, 2 math probability 4. There. Okay, so this should give us the same answer. And it does. And so hopefully that helps you use your calculator a little bit too and get you a little more familiar with how to enter these things into here. I know this video has been a little bit on the long. Sorry about that. I got cut off there, but I know the video's been a little bit on the long side. What the heck just happened? Where did my video go? I don't know what just happened, but I don't know what's going on here. Maybe I can turn that off. Hi, the end of this video has been a mess. I apologize. I still haven't figured out video editing. I'm doing everything on the fly here. So, anyways, this is the end of the video, and I will see you guys in the next lesson. So until then, keep your pencils and your wits sharp.